Assalamu alaikum wa rahmatullah. Good day, everyone, and I welcome you all to our mathematics class today. Remember, the course is MTH 101 General Mathematics 1, and this is a week 2 video. We have scheduled to create 2 videos, and this is the first one. This is why we say 1 of 2. The second one will follow for week 2. And our topic is advanced set theory. The video is always in line with the core curriculum minimum academic standard CCMAS developed by the National Universities Commission NUC. I, the presenter, am Shuaibu Muawiyah Salen Kano. Today's date is January 6, 2026. Now, here are the things we are going to learn on advanced set theory. The first one is set operations. 2, we are going to see the properties of union, intersection, and complement. In the first video, if you haven't watched the first video, I strongly recommend that you do. You can go to the channel. Under playlist, you will see videos on MTH 101. So the very first video there for week 1, we explain the meaning of union, intersection, complement with examples. In this second video for week 2, what we will do is we are going to see the properties of the union, the properties of the intersection, the properties of the complement, and we will give examples for those properties. The second thing we are going to learn is set operations. 3, we are going to see more about complement and set difference. Then we will proceed to Venn diagrams, visualizing set and operations. Finally, we are going to solve word problems with Venn diagrams. Okay, how do we use this Venn diagram to solve real world problems? Okay. Then we have learning outcomes. By the end of this lesson, whatever you are doing in life, make sure you know where you are going to. You know what you are trying to achieve. So in learning any topic you are learning, you should know the exact thing you are expected to learn, and what by the end of the lesson you are expected to do actively. Okay, so by the end of this lesson you will be able to do these 4 things enumerated. The first one here is you should be able to apply properties of union, intersection, and complement. Okay, and then the second one is perform set difference operations. Okay, if you are given 2 sets and you are asked to perform the difference between the 2 sets, you should be able to do that by the end of this video. Thirdly, you should be able to draw and interpret Venn diagrams. The Venn diagrams, what are they? How are they used? Okay, what do they mean? You should be able to do that. You give the interpretation, you also draw. And lastly, you should be able to solve real-world problems using Venn diagrams. We will all see that in this video, inshallah. Now, the next thing is properties of union. We are going. That's the first thing we are going to take. Properties of union. The first property is commutative law, or you can say commutativity. Commutative law. This means that the position of the set doesn't matter. Meaning, I can say A, I can mention A first, then union B, or if I like, I can mention B, union A. The result will not change. It's just like multiplication. If I have 2, assume this A is 2 and this B is 3. So 2 times 3 will give me 6. If I interchange them so that B is here, A is here, then I will have 3 times 2. And 3 times 2 will again give me 6. It will not change. We call this property commutative law. In basic mathematics operations, addition and multiplication are commutative. If I say 10 plus 15, it is the same as saying 15 plus 10. 10 plus 15 will give me 25. 15 plus 10 will also give me 25. So when I interchange the numbers, that will not change my result. And this is all about commutative law. Multiplication, if I say 10 times 20, I'm going to have 200. If I say 20 times 10, still I will get 200. So anyone that I put first and delete the other will not change my result. So A union B, the result will be the same as B union A. Okay, in basic mathematics operations, we have some operations that are not commutative. For example, 20 divided by 10 will give you 2, but 10 divided by 20 will not give you 2, it will give you 0.5. So division is not commutative. Division is not commutative. Similarly, subtraction is also not commutative. 10 minus 6 will give me 4, but 6 minus 10 will give me minus 4. 4 and minus 4 are two different numbers, okay, are two different quantities. So it's not the same, but multiplication and addition are commutative. Okay, so the next one is associative law. Associative law. Okay, this is when, remember, this is about union only, right? So you are going to see union everywhere. You see A union B, B union A. Now, what about associative law? If I have any three set and I am finding their union, I am adding their elements together to form a single set, then I can choose to take the first two, meaning I will perform operations for A union B, keeping C aside. When I am done with this one, the result that I got, I will now unite the result with C. Now, or I can say I can keep A and take the last two, B union C. I will now unite B with C first, and then I will unite A with the result that I obtained from here. So anyone I take is correct. I can start with A and B, unite them together, then finally bring C. The result will be the same as uniting B and C first, then adding the result to A. They will be the same. Nothing will change. Then there is idempotent law. Idempotent law. Idempotent law is when you have a set and is united to itself, meaning you have the same set operating on itself and the result will not change. You have A union A. A union A will still be A. Okay, you don't add. Remember, when you are uniting two or more sets together, if there is any element that is common to them, you don't add that element twice. You only add it once. Okay, let's say I have 3 in A, I also have 3 in A. At the end, I'm going to write only 1, 3. So the result will just be the same as just A. So it will not change. Then we have the identity law. Identity law is when you are uniting a set with an empty set. This is null set, empty set. There is no element at all in this set. It has not a single element. If I am adding this set to set A, okay, I am going to have the same A because I am not adding anything to it, no element here. So the result will just be the same as my A. The next one here is domination law. Domination law. This is when you have a set and you also have the universal set. You are uniting a subset, this subset, to the universal set. Remember that all the elements of A are also found in this universal set, and there are elements in the universal set that are not found in A. So if I am uniting A with the universal set, definitely my result will be the universal set. Okay, it will not change. Okay, examples of union properties. Now we are going to give examples. Remember, the first one that we gave was what was that? A union B is the same as B union A. Okay, that will not change. So we are going to see some of the examples. Okay, let's set A be a set of three elements 1, 2, and 3, and set B a set of three elements 2, 3, 4, 5. And the universal set, these two sets A and B, are obtained from the universal set, which has elements 1, 2, 3, 4, 5, 6. Now, if I am uniting A with B, A union B, so I am uniting all the elements that I have here, starting with the smallest one. So I bring it here. 2, I bring it here. 3, you see 3 appears twice, but I'm going to write only 1, and then I have 4, 5. Even if I start with B, then A, meaning I am uniting B with A, I will still have the same result, and that is why they say, okay, A union B is this, and this is the same as B union A. Even if I start with B, I will end up having the same thing. If I start with B, you see, I have 3 here, but I have to check set A. If there is a number less than 3, I have to begin with that number. So eventually I will go back to A and take 1 and 2, begin with them before considering these 3, and finally I have 4 and 5. So my result will just be the same. Then here is set A being united with the empty set. There is no element to be added to A to obtain the union, so the result will just be the same as set A. You see here, because this one has no element, so you have just 1, 2, 3, which is your set A. Another thing is, if I have set A and I am uniting it with the universal set, then I'm going to have the universal set, because all the elements in A are in the universal set. Look at A here, set A, 1 is here, 2 is here, 3 is here. So if I am uniting this, remember I'm going to take only 1. Let's take 1 here. You see, I will not write twice. I will have 1 only. 2, but I will only write 1. 3, I will only write 1, and then 4, 5, 6. You see, my result will be the same as the the universal set. So I'm going to have this universal set at the end. So A union, the universal set will be the same as universal set, which we call domination law. You see, domination law. And this is the identity law, the one for the null set. Okay, what about the properties of intersection? Okay, you can see that some of the properties of union are also the properties of intersection. Commutative law. A intersection B is the same as B intersection A. The order is not important, whether you start with A, then B, or B, then A, that will not change the result. Again, associative law that we saw previously, I can start by finding the intersection of A and B. The set that I obtain, I will then find its intersection with C. Or I'm going to keep this A and start with B and C. I will get the intersection of B and C. Then later I will unite, I get the intersection of A with my result. Okay, then idempotent law, A intersection A is the same thing as A, right? And then identity law, A intersection universal set is equal to the universal set. You are trying to get the the elements that are common to A and the universal set, but all the elements of A are in the universal set, so your intersection will just be A. Okay, then the domination law, if I have A intersection the empty set, remember this there is no element in the empty set. Okay, so the intersection will just be null again, will just be an empty set. Okay, because you don't have element in the universal set, so nothing will be common to them, so the result will just be nothing again. Okay, now we are going to see some examples on the properties of intersection, right? Examples of intersection properties. Okay, let set A be a set of 1, 2, 3, and set B be a set of 3, 4, 5. Okay, just as we used before, and this is our universal set. So we are going to find the intersection and see. A intersection B, the element that they have in common, see, they have 3 in common, right? They don't have 1 in common, they don't have 2 in common. The only element they have in common is 3. So A intersection B is 3. Again, if you want to find B intersection A, you are trying to get the elements that are found in B and A. Okay, and that will also be 3. So the result will still be 3. Right? So A intersection B is the same as B intersection A. No change. What about A intersection the union? Okay, you are looking for elements that are found in A and elements that are found in the universal set. Sorry, I said union. In universal set, I wanted to say universal set. So you can see that 1 here is also here, 2 is also here, 3 is also here. So all the elements here in A are also found in the universal set. So you end up having a set that is identical to set A. That is why we just say is equal to set A. A intersection universal set is the same as set A. Then A intersection empty set, as we said, there is no element in A at all, and because of that you don't have any elements that are common to them, and the result will just be an empty set. The next law is the distributive laws. So we can have union over intersection. We can also have intersection over union. Let's take the first one, the union over intersection. If I'm given any 3 set, okay, and I am asked to do this one, okay, I will find the intersection of B and C first. This will be a single set. Then I will unite the result with set A. If I do that, the result will be the same as doing it the other way, as given in the right hand side. Meaning, I will find the union of A and B, keep it. Union of A and C, keep it. Now I have 2 sets. Then I will now compare these 2 sets and see what elements do they have in common. If I have a set of those elements, the result will be the same as what I did here. Okay, so A union open bracket, you see union over intersection, right? That is why they say union over intersection. A union, then B intersection C. I will open the bracket and say, okay, this can be A union B, and I have it in bracket, then A union C in bracket, then intersection in between them. You see that? Okay. This is just like, let me show you something here. This is just like the way we open bracket. If you have 2 times open bracket x plus y close bracket, you know, you can say 2 times x. You see, 2 times x, okay, and then 2 times the other y, and look at the plus here, okay, the plus here. So 2 times x plus 2 times y. This is identical to what we have here. You see, let's say you have multiplication sign here, okay, and this is plus sign, this is multiplication sign. So this is same as 2 times b, then plus, you see, plus again 2 times c. You see, this is why the union appears here, and the intersection appears here. Then similarly, if I have intersection over union, the only thing here is I will bring this one here and this one here. You see, that is the only difference. I have intersection over union, so it's the same thing as A intersection B union A intersection C, meaning I can choose to find the union of B and C. This is a single set. Sorry about that. Then I find the intersection of this new set with my set A. Or alternatively, I can find intersection of A and B and keep it as a set, intersection of A and C and keep it as a set. Now these two sets, I'm now going to unite them together. If I do the union, the result will be identical as what I have here. Okay. So we are going to see some examples here for the distribution. Now for the distributive law, let set A be a set of only two elements, 1 and 2, and set B a set of two elements again, 2 and 3. Set C has 3 and 4. Now the left hand side for union over intersection, you see, as we said, here we will find B intersection C and unite the result with set A. Okay, so we are trying the left hand side. B intersection C, what elements do set B and C have in common? This is set B, this is set C, and we can see that they have 3 in common, so B intersection C will just be 3. You see, then this new set that has only 3 as its element, we are going to unite it with set A, and set A has just 1 and 2, so we'll just add the other element 3, so we have 1, 2, 3, a set of 3 elements. This is the left hand side. Now the right hand side say we can get A union B first and then A union C, then we find the intersection of the two sets. So let's begin. A union B, you are uniting set A with set B. You see, A has 1, 2 and B has 2, 3, so you have 1, 2 and 3. So 1, 2, 3, that is A union C. And then A union B, sorry, A union C, you are uniting A with C. So you have 1, 2, 3, 4. You see all of them together. Then you find the intersection of the result, intersection of this and this. So the first one is here, intersection, the second one, the element they have in common. You can see that they have 1, 2 and 3 in common, right? So the result will be 1, 2 and 3, and you can see that the right hand side is the same as the left hand side. You see, both sides equal, so it means that the distributive law is true. Okay, it's true, it's true. So we have the next one, complement laws, the laws about the complement of a set. Now if you have set A and you are uniting it with you are finding the union of that set A with the complement of A. Remember, the complement of a set is a set of all elements that are not in A but are found in the universal set. Okay, so all elements that are not in A are contained in this set. And then you have A again. So when you combine the element in A and the elements that are not in A together, you are going to have the universal set, right? You are going to have the universal set. So this makes sense. Then the second one says A intersection A complement. A complement contains elements that are not in A. Remember from the definition, right? So there will be no element in common to them, so the intersection will just be an empty set. Then we have the double complement. If you have A complement and then you are finding its complement, it will just be A. Okay, it may sound complicated, but if you think for a second, you find that's correct, because A complement, remember, A complement is a set of elements that are not in A at all. Set of elements that are not in A, but they are in the universal set. So if I want to find the complement of this A complement, it's like I am finding the opposite. Okay, I am finding the opposite. I will go to the universal set and extract all elements that are here and take the element that are not here. So if I take the element that are not here, I will end up having A. So that really makes sense. Then we have De Morgan's laws. Okay, De Morgan's laws says that if I have A union B, and then I want to get the complement, then I will just have the opposite. Everything will become opposite, meaning A here will become A complement, union will become intersection, and B will become B complement. Similarly, if I begin with the intersection, then A intersection B complement, the output will be identical as A complement. Then this one will change to, you see, everything is changing to opposite. The opposite of A is A complement, the opposite of B is B complement, the opposite of intersection. We are going to give examples on this De Morgan's law, and you will find out that it's fascinating, it's true. Example of De Morgan's law. Let's say we have a universal set that is a set of numbers from 1 to 6. 1, 2, 3, 4, 5, 6. And then we have set A, that's a set of 3 numbers obtained from the universal set 1, 2, 3. And we have set B, 3, 4, 5. All the elements here are found in the universal set. Okay. Now, the left side of De Morgan's law says A union B complement. So we have to find the A union B first, and then we find the complement of the result by comparing with the universal set. So A union B, we are uniting elements in A and in B together. So 1, 2, we bring the 1, 2. They have 3 in common. We are going to place only 1, 3, and then we bring the last element 4, 5. So we have A union B. So if we want to get the complement of what we got, complement of this A union B, then A union B close bracket complement will be equal to all elements that are in the universal set, but they are not in this. Okay, so we look at 1 is found here, this 2 is found here, 3 is found here, 4 is found here, 5 is found here. Only the last digit is in the universal set, but not here. So we are going to write that. You see, so the result is just a set of single element 6. Then we go to the right hand side. The right hand side say A complement intersection B complement. So we are going to find the A complement, the B complement, and then their intersection. A complement, remember, is a set of elements that are not in A, but they are in the universal set. A has 1, 2, 3. So we go to the universal set and remove the 1, 2, 3. We have 4, 5, 6. You see 4, 5, 6. Again, we find the B complement. B has 3, 4, 5. So we remove the 3, 4, 5. So we have 1, 2, and 6. So 1, 2, and 6 is the B complement. Finally, we get the intersection of our result. A prime, B prime, A prime intersection B prime. So this will just be 6. They don't have 4 in common, they don't have 5 in common, they do have 6 in common, and you can see that the result is identical to what we have here as the left hand side. Hence, De Morgan's law is successfully proved. Okay. Then set difference. After that, now we are taking set difference. What do we mean by set difference? Okay, by definition, the set difference is denoted as A minus B. Remember from basic mathematics operations, when we say the difference between any two numbers, we mean the result obtained after subtracting one of them from the other. Like if I said, what is the difference between 8 and 10, right? You will say 10 minus 8, the result will be 2. So that 2 is the difference. Difference can be positive difference, it can be negative difference in mathematics operations. Like the example I just gave is a positive difference. 10 minus 8 will give you 2. This is a positive difference, right? But if you say 8 minus 10 is also a difference, but the result will be negative, so we call it negative difference. The set difference, a minus b, or you can write it as a minus b, or you can write it a set minus b. This one is not pronounced slash, which is set minus. A set minus b, okay, is the set of elements in A that are not in B. You find all the elements that are in A, but they are not in B. So in set builder notation, we can say, okay, set the set difference A minus B is a set of all x such that, remember, you can also put, instead of this line, you can also put full colon, and it's the same thing, okay. A minus B is a set of all x such that x belongs to A, meaning is an element of A, and x is not an element in B. And that is the definition we gave here, right? Is the set of elements in A that are not in B. So it means our x here, okay, is an element of A and is not an element of B. So in set builder notation, this is how it is written. So we are going to give examples here. Let's say we have set A, and set A has this element 1, 2, 3, 4. Set B has this element 3, 4, 5, 6, right? So A minus B will be all the elements that are found in A and they are not found in B. So 1 is not in B, we write it. 2 is not in B, we write it. 3, look at 3 in B. 4 is also in B. So the only elements that are not in B but in A, okay, are 1 and 2. So our set difference is a set of 2 elements, 1, 2. Okay. More set difference example. Okay, let's say I have set A is a set of elements A, B, C, and D, and then we have set B is a set of elements C, D, E, and F. So the set difference A minus B will be elements that are in A and not in B. So you see we have A, B here that are not here. The C and the D are all found here. So we have A, B. And then another example, C is 2, 4, 6, 8. And then D is 1, 3, 5, 7. So set C minus D will just be the same as set C, because all the elements in set C are not in set D. So C minus D will just be equal to our C, right? Because no common element, right? Then look at this one. You have F, E. This is when you have equal set, right? E is equal to X, Y, Z, set of element X, Y, Z, and F is a set of element X, Y, Z. So when you say set E minus set F, you are going to have an empty set, because all the elements are common, right? All the elements are common. Okay. Now, what is the relationship between set difference and then complement, set complement? They say set difference can be expressed using complement, meaning A minus B is equal to A intersection B complement. Remember, B complement is a set of elements that are not found in B, but they are in the universal set. Even if those elements are in set A, it doesn't matter. If they are not in B, they are set complement. So now It means when you remove set elements that are in B, the result you have, you now take the elements that are found in A. Now those elements that are not in B but found in A gives you the difference between A and B, A minus B. Here is a little proof of that. They say X, meaning this is an element in the set difference. Okay, when you say A minus B, you obtain set of element X, right? Now X is an element of the set A minus B if and only if, this symbol means if and only if and only if X is an element of A, meaning is found in A, and X is not found in B. So if X is not found in B, it means X is found in B complement, right? Definitely is found in B complement. So we can proceed and say if and only if X is found in A and X is also found in B complement. So if X is an element of A and X is also an element of B complement, then it means X is an intersection of A and B complement. You see, so we can say if and only if X is an element or is a member of, okay, A intersection B complement, and this is why we say A minus B is equal to A intersection B complement. Okay, very interesting. Now we will see one of the most interesting thing about set, introduction to Venn diagrams. I love Venn diagrams so much. Okay, a Venn diagram, what is a Venn diagram? It's a visual representation of set using overlapping circles or other shapes, okay, to visualize the set. Okay, and we are going to see that right now. So we are going to see two subsets. We have the universal set and any two subset. How is that shown in a Venn diagram? Basic Venn diagram regions for two subsets with the universal set. Look at what is happening here. See, let me minimize this a bit so that you can see that. You see, so this, we have this circle for set A. All the elements of A are in this circle. Then we have this circle for set B. All the elements of B are in this circle. But we know that sometimes element can be found in A and in B, and this is why we allow the overlapping. If we have any element that are in A and in B, those elements will be in this region. Okay, elements that are in the universal set but they are not found in A, they are not found in B, so they will be outside here. Okay, now what about A complement and B complement? From here, how do we get the A complement? Now remember, we say elements that are in this circle, circle A, they are they constitute the element for set A. Okay, then everywhere outside this circle, including this region that is part of B, right, but is outside A, right? So all these regions outside A constitute A complement. Okay, and if you take B also, all the region outside B, including this region that is in A, it's not in B, right? It's not in B. So including this region that is in A but not in B, okay, and the region outside here constitute B complement. And then this is where we have A intersection B, where you have element of element common to A and B. So how many regions do we have here? Okay, we are going to see in a moment. There is what we call element in A but not in B. Where are they located? And how do we write them? You can see this is the region. You see, here you write element, this region you write elements that are in A but not in B. Okay, but remember we say that all the elements that are not in B, okay, they constitute the B complement. So all the region outside here, including this region, constitute B complement, and this is why we have to say A intersection B complement, where our A, okay, the element in A, okay, are also found in B complement. Okay, they have them in common. So this region is part of B complement, and this is why we say A intersection B complement. The next region is where you have B only. Can you see? So this region is part of A complement and is also in B. So we are going to say B intersection A complement. Okay, elements that are found in B, okay, but not in A. And here elements that are found in A but not in B, right? Then the third region is where the two sets agree. Okay, A intersection B. You see the region A intersection B. This is the region. So there is no complement, if you can see here, right? There is no complement. You can see that there is no complement here. Then the last region is outside. Remember, this region that we see here outside, the region that we see here outside, okay, is A complement and is also B complement. So this is where the two sets agree outside. Okay, the B complement agrees with the A complement, meaning they have the element in common. This is why we say A outside here is A complement intersection B complement. Okay, so you can see that we have four regions. We have region where we have A only, we have region where we have B only, we have region where we have A intersection B only, and finally we have region where we have A prime intersection B prime. So for only two sets, you have four regions. You see all four regions of the universal set. Now what if I have three subsets with the universal set? Identifying the three subsets. Now you see, you draw circles and allow them to overlap. Okay, this is our set A, you can see that, and then this is our set B. Finally, this is our set C. Okay, now how many regions do we have? We are going to see that in this case we will have 8 regions, and we will identify them one by one, right? We'll identify those regions one by one. Okay, the first one is element in A but not in B or C. Where do we have that? This is where we have it. A intersection B complement intersection C complement. This means this region, you are recording elements that are in A but they are not in B, they are not in C. They are in B complement, they are in C complement. They are in B complement because this region is outside B, and outside B is part of B complement. They are C complement because this region again is outside set C, right? So they are part of C complement, and that is why we say A intersection B complement intersection C complement. Otherwise read as element in A but not in B or C. Then the next one is element exclusively in A or exclusively in B. Exclusively in A meaning you have them in A only. So we did that before. We are going to keep, we kept the result. Now we will see exclusively in B. They are in B only, not in A, not in C. And the region for that is here. You see, this is where you have elements that are in B but they are not in A, they are not in C. They are in A complement because this region is outside A. You see, this is circle A. It doesn't extend to this region, so this region is outside A. This region is also in C complement because it is outside C. So A prime intersection B intersection C. You see that we do not put prime on B because it is inside set B, inside the circle of B. So all elements that are exclusively in B but not in A, not in C are placed here. This is the region for that. Then we are going to see element in exactly one of A, B, C. For this one and this one, we did them before. Now we focus on this one. What about the C? This is the region, right? This is where you don't have this region. You don't have A, you don't have B. What you have is C. But because they are outside A and B, they are part of A complement, they are part of B complement, right? This is why we say A prime intersection B prime intersection C, right? So element exclusively in C are written here, exclusively in B are written here, exclusively in A are written here, and this is the notation: A intersection B prime intersection C prime, A prime intersection B intersection C prime. Okay, remember the commutative law. I can bring this one here, as I can start with B here and bring A here, so that B intersection A prime C prime is all the same. Okay, even this one I can choose to bring C here and say C intersection A prime intersection B prime. The result will be the same according to the commutative law that we just learned. Okay, we have just identified 3 regions successfully. Then what if we want to find element in both A and B but not in C? Which region? Element in A and B but not in C. You see, this is the region, right? In this region is part of A. Okay, it is part of B but it's not part of C. You see, C stopped here. So this region, you put elements that are in A, they are in B but not in C. This is why we put C complement, right? Then the next one is element in both A and C but not in B. Which region are we dedicating for that? A and C. You see, this is the region here. We have A here, we have C here. Okay, but B did not extend to this region. So in this region we have A intersection, this one should have been here. Okay, but I don't want to make it so small that you hardly see. So A intersection B complement intersection C, meaning elements that are found in A and C but not in B, because this is outside circle B. Then the next one is element in both B and C but not in A. Where do we write that? They are not in A. So this is the region. You see, this region is inside B. This region again is inside C, but it's not inside A. A did not extend to this region. So elements that are not found in A but are found in B and C, right? Then the next one is element in all the 3 sets, element in all 3 sets A, B and C. Now this will be the middle. You see the middle here, this region. You see, this region is in B, is in A and is also in C, all of them together, right? MashaAllah. Finally, we are going to see where do we write elements that are not in A, not in B, not in C. It has to be outside here, right? Outside here is part of A complement, is part of B complement, is also part of C complement. So this will be A complement intersection B complement intersection C complement, as you are going to see here. You see, A complement B complement, C complement, intersection of all that. So with that, we have all the regions of the universal of the set, and if you count the number of regions, you see that you have 8. You see 1 2 3 4 5 6 7 8. Okay, now we are going to give examples here. We are going to give example. We have to give example. Now our example is on distributing elements in the Venn diagram. Here are the given set. Let the universal set be a set of numbers from 1 to 10. We have 1 2 3 4 5 6 7 8 9 10. And then let set A be set of element 2 3 4 2 3 5 7, all of them from the universal set, and then B a subset 3 5 6 8 9, all the elements of B are also from the universal set. Now we need to distribute all elements of the universal set into the 4 regions, because since we have only 2 sets, as we showed few minutes ago, that when you have the universal set and you have only 2 subsets, you are going to have 4 regions. So we are going to distribute the element in the 4 regions. We are going to see the element in A only, which will be A intersection B prime. We are going to see element in B only, which is B intersection A complement. We are going to see element in both, which is A intersection B. Then we are going to see elements that are in neither. They are neither in A nor in B. So will be A complement intersection B complement. Okay. Find element in A only. Okay. Finding element in A only. Elements that are found in A only. Okay. So okay. Now remember, this is A intersection B complement. So to find those elements, what you do is you have A, right, and you also have B, right? So you are going to say A intersection B complement. How do you find the B complement? They say this is equal to element in A but not in B. Yeah. So this means I have to say the element in A set minus element in B. Okay, elements that are found in A only but they are not found here. So comparing the two, this 2 is not found here, but 3 is found here, 5 is found here, 7 is found here. So these are the only elements that are in A but not in B, right? So it means that my result is A intersection B complement will just be 2 elements. So I'm going to place these 2 and 7 in that region, and you see this is the region. This is the region that you have A only, not in B. So 2 and 7, I place them appropriately. Now the next one that we are going to see is element in B only. Okay, this will be B intersection A complement. I have this set of element for A. I have this one for element that shows element in B. Then I want to find B intersection A complement, meaning now I will find element in B but not in A. Element in B but not in A. So this is the same thing as element in B set minus element in A. Okay, now I will choose element that are here but they are not here. So 3 is here, I will not take it. 5 is also here, I will not take it. 6 is not there, it's not here, so I will take 6. 8 is also not here, I will take it. 9 is also not here. So these 3 numbers, they are the elements that are in B but they are not in A, right? So what my result is B intersection A complement is a set of 3 elements, 6, 8, and 9, and I will go to that region and write those numbers. You see, 6, 8, 9. So I got elements that are in A only, I got elements that are in B only. Now the next thing I am going to do is to find element in both A and B. How can I get the element in both A and B? Now finding A intersection B. This is the set of elements here that are in A, and this is the set of elements that are in B. Now A intersection B means element common to both A and B. So I will bring set A, look at set A here, I bring it here, intersection, I will now bring set B. You see, this is set B. So what do they have in common? 2 is not found here. 3, of course, you have 3 here, you bring it. And then 5, of course, they have 5. 7 is not found here. So the only element they have in common are 3 and 4 and 5. So we have set of 2 elements, 3 and 5. Our result is A intersection B is a set of element 3 and 5, and we go to that region and write the element 3 and 5. You see, this is the region where they meet. So 3 and 5. Finally, we are going to find elements that are not in A, they are not in B. So they will be outside here. They are in the universal set, so they will be here. Okay, because this rectangular shape, okay, enclose all elements of the universal set, okay, whether they are in A or B or not. Okay, so how do we do that? Find elements in neither A nor B. That is finding A complement intersection B complement. What you are going to do now is you bring the universal set. It's a set of elements from 1 to 10, right? So you find A union B. You find A union B. Set A, these are the elements for set A. You are uniting those elements with the elements that you have in set B, right? So if you unite, starting with the least number you have here is 2, so you bring 2 here. Then 3 are found here, and here you write only 1. 4, we don't have 4. Then 5, okay, 5 is found here, and here you write 5. 6, there is 6 here. 7 is found here. 8 is found here. 9, that is it. So after uniting this, remember, this now gives you a set of all elements. The elements that you have here, all the elements that you have here, they are either in A or in B or both. That's the meaning of the union, right? We learned union in our previous video. So after uniting them, you have all the elements that are found either in A or in B or in both. So now you take this now and subtract it from the universal set. The remaining will now be the set of elements that are not in A, that are not in B. And that is what you want. So you bring the universal set, then set minus the union that you just obtained. This will give you A complement intersection B complement. So this is my universal set. You bring this element here and place it, then set minus A union B. You just did the A union B. You've just done the A union B and you obtain this. So you now select elements that are in the universal set, but they are not in your A union B. So 1 is not here, you write it, but 2 is there, 3 is there, 4 is not here, you write it, 5 is there, 6 is there, 7 is there, 8 is there, 9 is there, finally 10 is not there. So you have 1, 4, 10. So you go to that region and write the element 1, 4, 10. You see, we have successfully distributed all the elements. Okay, now we are going to do some verification, some check to make sure that what we have done is correct. Now if you want to check your result, you unite all the elements in the 4 regions. Okay, check that all the elements of the universal set are accounted for, meaning you distributed the element into different regions, right? After uniting them, you have to get the universal set back. So you have elements that are in A only, not in B. You unite that with the element that are in B, not in A. You unite that with the element that are both in A and B, and then you unite that with the element that are neither in A nor in B. For A only, we got 2 and 7. For B only, we got 6, 8, and 9. For A and B, we got 3 and 5. For neither A nor B, we got 1, 4, 10. So if you unite all of that, you will get the universal set back. You see, 1, 2, here is 3, where is 4, 4, 5, 6, 7, 8, 9, 10. So you have all your numbers back, which constitute the universal set, right? So this makes sense. Now you can also check the verification by finding the cardinalities, the number of elements in each of the 4 regions, right? For A only, you have only 2 elements. For B only, you have 3 elements. For A intersection B, right, you have 2 elements. For neither A nor B, you have 3 elements. So if you get the total of these, 2 plus 3 plus 2 plus 3 will give you 10, and that is the cardinality of your universal set. Your universal set has 10 elements. You see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 elements in total. So you can check by trying to get the actual element in the universal set. You are going to find that they are retained, okay, they are not changed. Or by checking the number of elements in the universal set. The number of elements in the universal set is 10, so the cardinality will be 10, right? Okay, what if we have 3 subsets? So how do we distribute the element? We are going to give an example for distributing element in 3 set Venn diagram, where we say we have 8 regions, right? 8 regions. So how do we distribute the element in those 8 regions? We're going to give examples. Now the given set is here. Let the universal set be. For the universal set, you have set of elements from 1 to 15. Okay, natural numbers, counting numbers from 1 to 15. Then set A has this element 1, 2, 3, 4, 5, 6, 7, and set B has 3, 4, 5, 8, 9, 10, 11, and then you have subset C 5, 6, 7, 10, 11, 12, 13. Very interesting. So we have the universal set, we also have the 3 subset. Okay. What are we going to do now? We need to distribute all elements of the universal set, or the 15 elements given, into the 8 regions, right? We are going to find elements in A only, that is A intersection B prime intersection C complement, an element in B only, element in C only, element in A and B only but not in C, A and C only but not in B, B and C only but not in A, and then element in all the 3, A intersection B intersection C, an element in none, neither in A, B nor in C, right? Okay, solution. The first thing we are going to do is to draw the Venn diagram with the overlapping circles. You see, so this is our set A, this is our set B, and this is our set C. Okay, now we start the distribution. Okay, find element in A only. This means I have to find elements that are in A but not in B and not in C. Okay, So remember, here are our elements. A intersection A is a set of this element, B is a set of this element, C is a set of this element. So to find A intersection B complement intersection C complement means you are finding element in A but not in B or C. So what you gonna do? You are going to find B union C first. You see, if you unite B, remember the interpretation. I like, going by the definition. You want to find elements that are in A, but they are not in B, they are not in C. So what you will do is you unite all the elements that are in B and C, and then you subtract those elements from A. You see, so element in A but not in B or C means A set minus B union C. So you unite the B and C, and then you subtract that from A. So here it is, your element in A, look at them here, all of them are here. Then set minus, then you unite B, element in B union element in C. So if this one you bring it down, then set minus, now you unite these together. The least number here is 3, then you bring 4, 5 is here, you write it 1, 6, 7, then what about 8, 9, and 10, 11, and then 12 and 13 are found here. So you united them here. So finally you select elements that are in E but they are not in this one. This has united all the elements that you have in B and C, and you don't want them in your set. So if you compare with this, you find that 1 and 2, they are not in this. So 3, 4, 5, 6, 7, look at them, 3, 4, 5, 6, 7. So only 2 elements are not there. So it means A intersection B complement intersection C complement will just be this. So you go to that region and write the 1 and 2. You see, this is the region, as we explained earlier, where you have elements exclusively in A but not in B and not in C. So we write our 1 and 2 here. Then the next thing is we find element in B only. B only, they are not in C, they are not in A. Okay, so this will be B intersection A complement intersection C complement. So as usual, we are going to find the union of A and C and subtract it from B. Now A is a set of this element, B is given, C is given. So finding A intersection B, finding B intersection A complement intersection C complement means element in B but not in A or C. Now we are going to find the union of A and C and subtract it from set B. So this will be B set minus, okay, A union C. Now we bring our set B here. This is set B. You see, from 3 to 11, we bring it here. Then set minus, okay, then open bracket as given here. Then our set A, look at set A here. So you bring set A here. Union set C, you bring set C. So you unite set A and set C. 1, 2, 3, 4, 5, 6, 7. Okay, you have the 5, 6, 7 here, you don't repeat them. Then you move on 10, 11, 12, 13, 10, 11, 12, 13. Now you compare the two and select elements that are in B but they are not in this, right? And those elements will only be 8 and 9. 3, look at 3 here, 4 is here, 5 is also here, but 8, 9 are not here. You see, after 7 you just have 10. So you have 8 and 9, but 10 and 11 are all found here, so we leave them. So we have only 2 elements again, only 2 elements again. Okay, 8 and 9. So we go to that region that we have B only. You see, we write 8 and 9. Interesting. Moving on, we have just done for 2 regions. Okay, moving on, we find element in C only. So as usual, we are going to find the union of A and B, the union of A and B, and then subtract that from C. So A equals this, B, we are given all these three. So we want to find C intersection A prime intersection B prime, meaning we want to find element in C but not in A or B. So this means we are going to unite the element in A and B and subtract that from C. So it will be C set minus A union B, right? So our C is a set of these elements, so we bring that here. Then set minus open bracket, set minus open bracket. We bring set A, you see set A here, we bring it here, followed by union, we put the union, followed by set B, this is set B, so we write our set B here. Then we now unite our A and B here, right? 1 2 3 4 5 6 7, and then this one has the 3 4 and 5, all of them we have written them, so we ignore that. Then 8 9 10 11, so 8 9 10 11. So we have united the set A and B. Now we want to subtract that from set A. We select elements that are in A but they are not here, right? 5 6 7 10 and 11. Look at them here, 5 6 7 10 11, they are all found here, so we don't take them. 12 and 13 are the only elements that are found in C but not in our union, so we take 12 and 13 and we go to the region for C only and write the 12 and 13. Look at the region down here for C only, 12 and 13 successfully. Now the next thing is we want to find elements that are in A and B only. They are not in in C, right? They are in A and B but not in C. So here are our three sets. So to do that, this means we are going to find A intersection B, okay, and then we subtract set C from that, okay, because of the complement that we have here, element in both A and B but not in C. Now by comparing elements in A and B, we want to find element common to them. Okay, here is what they do. They just substitute, you see, open bracket, and then you have A element in A intersection element in B, then set minus C, you bring the element in C. Okay, now find the intersection of these two sets, the elements they have in common. 1 is not found here, 2 is also not found here, but 3, can you see 3 4 5, 3 4 5, they are found here, so you write them, but 6 and 7 are not found here, so this is the intersection. Now you say a set minus this one, you see this one. Now you want to select elements that are in here but they are not here. 3 and 4, they are in your intersection but they are not here. You see this 5 is found here, so you are not taking that, so your answer is 3 and 4. So this means my A and B only is a set of two elements, 3 and 4. So I go to that region for A and B only. You see this is the region for A and B only, so I have 3 and 4 written there. The next one is I want to find A and C only. We want to find A intersection C intersection B prime, meaning we want to find elements in both A and C but not in B. So we will find the intersection of A and B, okay, then minus set B. Now this will now be, we bring for open bracket, we bring set A, we give it here intersection, we bring set C, okay, close bracket, then set minus B, we bring set B. Now what elements are common to this one? You find out that 5 6 and 7, look at 5 6 and 7, they are the only element common to the two sets, So you write them 5, 6, 7. Then set minus, you bring the last one, you bring it here. Okay, you select elements that are in here but they are not here. Look at 5 is here, is also here, so we don't take it. 6 and 7 are not found here, so we write the 6 and 7. So it means our result is a set of 6, 7 as the only element. So we go to that region. You see, this is the region where you have A and C only. You see this? So you write your 6 here, you write your 7. Okay, moving on. Wow, we are making a significant progress. Find element in B and C only. So you are going to find B intersection C and then you subtract A from that. So again, these are your 3 sets. You find B intersection C intersection A prime, meaning element in both A and C but not in A. Sorry, element in both B and C but not in A. So this is equal to, you open bracket, B intersection C minus A, right? So you bring set A, B, and then intersection set C, you bring it, then set minus A, you bring that A there. So you find elements that are common to these two sets, and by comparing you'll find that 5, 10, and 11 are the only element. 5 is here, 5 is here, 10 is here, 10 is here, 11 is here, 11 is here, right? The remaining elements are not found in both. They are either here, not here, or here and not here. So we have 5, 10, 11. Then you bring this one, set minus this one. Now you select elements that are found here, but they are not here. So the only element are 10 and 11. This 5, see it here. So it means that region will have only 2 elements, 10 and 11. This is our result. So we go to the region for B and C only and write 10 and 11. You see, this is the region for B and C only. So we write our 10 and 11 here. Okay. Wow, we are almost done. It's like we have only 2 regions left. So the next step is we find element in all the 3 sets. So you are finding A intersection B intersection C, right? So this is what you do. You have A intersection B intersection C, element common to all of them. So you write set A intersection set B intersection set C. So the first thing you do is to find the intersection of the first 2 of A and B, right? You write the result and then you find the intersection of that result with C. You see, so you can see that they just brought the C here and then they found the intersection of A and B. The elements that are common to A and B are 3, 4, 5. You see, 3, 4, 5, 3, 4, 5. This 1 and 2, they are not here. 6 and 7, they are not here. So only 3, 4, 5 are common to them. So they wrote 3, 4, 5, and then they brought this one here, right? Now you find element common to this one and this one. 3 is not here, 4 is not here, but you see 5 is in both. So your answer will now be a set of a single element 5. So your result for A intersection B intersection C is just 5. Now you go to that region, which is the middle one, and write 5. You see, 5 is written here. So we have successfully completed for all the regions within the 3 circles. Now we have to find for the region outside, right? So how do we do that? Look at it. Find element in none of the set, the region for none of the set. Now finding A prime intersection B prime intersection C prime. So now what you will do is you have the universal set that has all the elements, right? And remember, all the 3 elements are obtained from the universal set. So you unite A, B, C. You find the union of all of them. Is set A union set B union set C. This is your set A. You are uniting that with set B, and you are uniting that with set C. So you start from the least number. The least number is 1, then 2, 3, 4. Even though the 4, look at, they are found here, but remember we are writing them once. 5, 6, 7, right? Then from here I can get 8, 9, 10, 11. Okay, 5, 6, 7, 10, 11. I have written them already, so I will not take them. Then 12 and 13. I write 12 and 13. This is now your A union B union C. So if you want to get neither in A, B, nor C, then you have to say universal set minus then the union that you obtain. You combine all the elements of B and C, A, B, and C, right? All of them, you have it in a set. So you subtract this one from the universal set. The remaining will be a set of elements that are neither in A, nor B, nor C. Interesting. So when you do that, you see, you are going to have 12, 14, and 15. You look at elements that are in here, but they are not here. You see, the elements that are in the universal set that are not in your union are only 14 and 15. But from 1 to 13, all of them are found here. You see that? The remaining will just be 14, 15. So 14, 15. And that region, remember, is outside the circle. So you go to that and write, you see, 14, 15. So we need a round of applause for this. This is a tremendous achievement indeed. Wow, 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 wow. This is interesting. Now, how do I verify that I am right? We can verify all the elements by uniting all the regions. Remember, we have 8 regions: 1, 2, 3, 4, 5, 6, 7, 8, right? This is A only, this is B only, this is C only, A and B only, A and C only, B and C only, A, B, and C together, and then neither A nor B nor C. So all the elements there, we can bring them. For A only, this is what we got. For this is what we got. You unite all of them together, right? The last one, remember, for neither A nor B nor C, we got 14 and 15. So if you unite them, you see you have 1 here, 2 here, 3 and 4 here, right? Where is 5? 5, 6, 7, 8, 9, 10, 11, 12, 13, and finally 14, 15. So you have all the numbers together. So we are right. We successfully distributed all of them, okay, appropriately. So you can also check by cardinality, the cardinality of each one of them, meaning the number of elements they have. This one, for A only, you have 2 elements, B only, you have 2 elements only, and the last one also, you have 2 elements only. Remember, for A, B, and C, you have only 2 elements, only 1 element. And I think that element was 1, right? It was 5. You see, 5, only 1 element comes to all the 3 of them. So if you add these numbers, this cardinality, if you add from 2 to these 2, you add them together, you are going to have 5 and 15, and that is the cardinality of the universal set, because it's a set of 15 elements from 1 to 15, right? Now the next problem we are going to see is a word problem involving 2 subsets and the universal set. Okay, we are going to see how Venn diagrams are effective in solving real world problems, right? Okay, we are given here this is the information given information. In a class of 50 students, 30 like mathematics, 25 like physics, 10 like both subjects. Okay, Now we are going to find how many like only mathematics. The reason is that part of these 20 who like mathematics, these 20 who like mathematics, some of them like physics. Also, the 25 who like physics, some of them like mathematics. So we are going to find those among these 30 who like only mathematics, and those among these 25 who like only physics, and those who like neither subject. They don't like mathematics, they don't like physics. And this is why you will see that when you add the numbers, 30 plus 25 will give you 55, and then plus 10 will be 65, which is more than 50, right? The reason is that the 30 here are not the people who like only mathematics. It's a total of those who like mathematics and physics, and then those who like mathematics only, right? We will see that very soon. So how do we use the Venn diagram to do that? We can see that the 50 here is the total, so this should be our universal set. So we are going to say let M, we take the first letter here, M, for set of mathematics, and then P for set of set of physics, sorry. So this means we have two subset and the universal set, and as we have shown earlier, the regions will be 4 regions, right? In the Venn diagram. So let's see that. The first thing we do is to define set and region. Okay, setting up the Venn diagram. So let our letter M represent the set of students who like mathematics, and then capital letter P, set of students who like physics. And then we have the universal set of all students in the class, and this is 50 as given. Okay, the number of students who like mathematics will be is 30 according to what we are given, and for physics we have 25, and those who like mathematics and physics are 10 students. Okay, now you see here is our Venn diagram. In the Venn diagram, you see we know our universal set, right? So we put 50 here. We know M intersection P, those who like both, this is the region for them, so we put 10. But we don't know those who like only mathematics, so we put letter X for that. We don't know those who like only physics, we put letter Y for that. We are going to find that. And we don't know those who like neither mathematics nor physics, outside region, right? We don't know that either, so we put Z, and we are going to find our X, Y, and Z. Okay, moving on, they say where X is only mathematics, Y is only physics, and Z is neither subject, right? So the first one is we are going to find our X. Find student who like only mathematics. Remember what we said, that the total for the student who like mathematics, the total that we are given M, is actually a total for 2. Those who like only mathematics and those who like both mathematics and physics. So when you do that, you see the total is 30 is equal to only mathematics. We don't know. This is the region that we put X. So we put X there in our equation, and then plus those who like both subject are 10. So we have 10 here. So from here we can subtract 10 from 30. Our X is 30 minus 10, so X is 20, right? So it means a student who like only mathematics, that is M intersection P complement, right? The cardinality of that is 20, right? We have 20 people. So we now give an update for that and say, okay, now we know our X. We will no longer write X here. We know the X is 20, so we put 20. Okay, update. Only mathematics, we have 20 students. And then we proceed to get Y, the student who like physics only. The number that we were given It was for those who like physics only and those who like both physics and mathematics. So we'll follow the same method to get our y. Find students who like only physics. Okay, calculating P intersection M prime or P intersection M complement. So the total in P, which we were given 25 for, include only physics and both math and physics, right? So only physics, we don't know, we put y, plus both math and physics we are given 10, so we put 10. So our y will now be this 25 minus 10, and we get our y as 15. So now our result is students who like only physics, their total, their number, okay, cardinality, P intersection M complement is 15. So we now remove that y and put 15 in its place. We know our y x and we know our y now. So then we proceed to get our z, right? Update physics is 15 students, right? Find student who like neither subject. So remember, for the total student we were given 50, right? So this 50 includes only math, only physics, right? Plus both, then plus neither. Okay, only math, only physics, both, then plus z. It should be plus neither. I forgot to write that, I'm sorry. There should be plus neither. Only math, we got that 20. Only physics, we got 15, plus both is 10, then neither, okay, is z. So we add that z, right? The first equation is incorrect. There should be plus neither here, okay? Then we now add 20 plus 15. This will be 35 plus 10, 45. So on the right hand side we will have 45 plus z, right? So 50 equals 45 plus z. Then our z will be 50 minus 45. So we get 5. 5 students did not like mathematics, did not like physics. So and that is the outside region, right? Student who like neither subject equals that is M complement intersection P complement. This will give us 5. So we have an update. So instead of z, we know our z is 5. So we write 5 there. So with this, we found for all the 4 regions, 1, 2, 3, 4. Okay, all the 4 regions, neither subject 5. So how do we verify? You can verify in different ways. You can verify by using union formula, right? You the M union P. If you unite all of that, okay, you are going to get 45, because 45 is the number of students who like mathematics and physics, or at least they like one of these subjects. So this will be mathematics plus physics minus the intersection of P and Q, because as I said, this intersection is found in both. So when you add that, when you add the two numbers for math and physics, you subtract the intersection, right? So when you subtract that, you have 45. Okay, and the total will now be those who like at least one of the subject plus those who do not like anyone. So those who like at least one, you got 45. Then okay, those who like at least one of the subject, you got 45, plus those who like neither, that was 5, right? We got 5 here. Where is it? You see, for those who like neither. So when you add the 45 to 5, you have 50, and that is the universal set. There, this is not part of the solution, okay? We are checking to make sure that, yeah, our answer is right. If there is any mistake, we will go back and check our result again. Okay, an alternative way of checking, they say alternative check, is you can take only math plus only physics plus both plus neither. This is only math, we got 20, plus only physics we got 15. For math we were given 10. For neither we got 5. If you add all these four numbers together, you are going to have 50, and that is your universal set, right? So we are right. Final answers. You remember we were asked to get, this is like a summary of our answer. Okay, we already got our answers, right? We want to combine them together to give a quick concise summary. Okay, for only mathematics, this is M without P, we got 20. For only physics, that is P without M, we got 15. For neither subject, neither math nor P, okay, we got 5. That was our solution, right? And here we got the Venn diagram. Only math, only physics, both math and physics, neither math nor physics, and then our universal set 50. That was our result. Now we will now go to problem 2. Problem 2 is for the word problem is also about two subjects, but the intersection is not known, meaning those who like mathematics and physics together, we don't know, and we are expected to find that. How do we do that? You know, in the previous one, the one we've just completed, we were given the number of students who like both subjects, right? What we were not given were those who like physics only or mathematics only or neither. But those who like both, we were given that. But now we were not given those who like both. How do we find them? So here is the problem again. The same problem, only that one quantity is missing. The 10 that we were given for both subject, right? In a class of 50 students, 30 like mathematics, 25 like physics, 5 like neither subject. So we're going to find those who like both subjects, right? And then how many like only mathematics, how many like only physics. Okay. Here is what we are going to do. As usual, we are going to say we are going to define the set and regions. We are going to say let P be the set of students who like mathematics, and then P for those who like physics, and our U for the set of all students in the class. This is our universal set. The number of students who like mathematics, you see there are many ways of writing cardinality. Either you use these two vertical bracket, okay, or you write it like this: n open bracket, capital M, you give the set name, and then close bracket. It all means cardinality, the number of elements in that set. So the number of elements in set M, in the circle of M, or everything there is 30. For the circle of P is 15. For the universals, 25. For the universal set, we were given 50 for the whole rectangle there, right? Then those in the region considered neither P nor M is 50. So what we don't know is the intersection of P and Q. The number of M intersection P is what we don't know. So let X represent that, the unknown we need to find. So we then draw the Venn diagram. As you can see, if we draw the Venn diagram, we put our X here for both that we don't know. But remember what we said, in this region is for math only, and this is for physics only. So you get the number that you were given for the whole circle, you subtract X from that, so it will give you math only, because part of this 30 also like physics, part of this 25 also like mathematics. So you have to subtract from this 25, you have to subtract S from 25 to get those who like physics only. Here too, you have to subtract to get those who like mathematics only. For the neither, we were given from the problem as 5 students didn't like any of the two subjects. Okay, So this is what I just explained. 30 minus x is only mathematics, since total in M is 30 and x is in both, right? Is in both. And then x is both mathematics and physics, is the unknown quantity. 25 minus x represent only mathematics, and 5 is for neither subject and is already given, right? Okay, now how do we find, we have to find the x first. So how do we find the x? Interestingly, we know the universal set, right? The cardinality of the universal set is 50. Okay, so we are going to add everything together. We add the set of equation using total, that is for the universal set. We know the total is 50. Using total number of students, the sum of all regions must equal the total number of students. So you have 4 regions. Remember, you have a region for only math, region for only physics, region for both math and physics, and for neither. You add all this together and you say it's equal to the cardinality of the universal set. For only math, you have 30 minus x. Where is it? You see, look at it. 30 minus x for only math. For only physics, 25 minus x. Right? For both is x. For neither, 5. You add all these quantities together and then you equate that to 50. You see, only math, only physics, both, you don't know both, so you put x, plus neither is 5 is equal to, now you are 50, right? So you can now clear the brackets. You open the bracket. This is 30 minus x plus 25 minus x, then plus x plus 5 equals 50, right? So you add the numbers. 30 plus 25, this will be 55. 55 plus 5 will give you 60. Then you come to the latest, minus x plus x. This is the same thing as x minus x, so this cancel is 0. You are left with this minus x, so you put the minus x here. Now you solve this equation for x. So you bring this equation here, same thing, and solve for x. What do? You take this 60 to the other side. It will become minus 60, right? And this side you will be left with minus x is equal to this 50. You bring the 50 here. When it crosses the equality sign, it will its sign will change, so it will become minus 60. Again, you keep your minus x is equal to 50 minus 60 will give you minus 10. Now this minus cancel this minus and you have x is 10. So you see we got our 10, right? So 10 students like both subjects. From here, my only math is just 30 minus 10, since I know my x is 10 now, right? 30 minus 10 will be 20, right? And then 25 minus 10, 15. Now I know everything, and this one is 10. So with this information, I can fill everything. You see, 20, 15, 10, and 5. So both subjects, we got 10. We got 10 students who like both subjects. Now moving on, look at they say find students who like only mathematics. You see, we now now that we know the intersection, the number of n intersection p, we know this is 10. We know that this for math only, it should be the total for math minus those who like math and physics, right? So this will be 30 minus 20 minus 10, and then we have 20, right? So our result for those who like mathematics only, their number, okay, is 20. So again, you see we have the update, and this is 20. Now if we want to get those who like physics only, again, this is like a repetition, another way of doing it, okay? But we already solved the problem, right? But we are showing the mathematical way of writing the problem, solving the problem, sorry. So how do we calculate this? Those who like math only without physics, okay? the intersection is 10, so physics only without math is equal to total who like physics all together minus those who like mathematics and physics. So the total was 25, then we say minus 10. 25 minus 10 will be 15, so we got our 15. Students who like physics only will now be a number of P intersection M complement, and that is 15. So again, you see the 15 here. The purpose of repeating this is to show you the update after every solution, right? So all values are now calculated. Now, how do I verify? Remember my total. The first thing is I have to unite my M and P, just as we did before. My math and physics. This will be number who like math, number who like physics minus the intersection. The reason is that the intersection appears in this and this. Okay, we have to keep only one, so we subtract 10. So 30 plus 25 minus 10 will be 45. 45 like at least mathematics or physics or both, right? But those, if we want to get the total for the entire universal set, then we bring this union plus those who like neither math nor physics, that is M complement intersection P complement, and their number was given as 5, so we add 5 to the 45 that we got, and this will be 50. That is the number of elements in the universal set. Okay, now alternative way of checking is to add the regions. You have 4 regions, 1 2 3 4. Math only without physics, physics only without mathematics, both mathematics and physics, neither mathematics nor physics. So for math only you have 20, physics only you have 15, both you have 10, neither you have 5. Add these numbers and you will have 50. See that? Very interesting. So what will be our summary, the summary of our answer? We were asked to find 3 things: both subject, only mathematics, only physics. So for both subject, that was the intersection, we got 10 students. Only mathematics, we got 20 students, and only physics, we got 15 students. Interesting. So again, this is the Venn diagram, okay, with all the 4 regions, 1 2 3 4, and we have our universal set 20. Very interesting. You see the verification, add all the numbers you have inside, you have the 50 there. Okay, great. Now we are proceeding to word problem 3. When you have 3 newspapers, the purpose of this is to show you how we can use a Venn diagram with 3 circles, right? 3 subsets. How do we use that in a word problem? In a survey of 100 people, you see from here we know our universal set 100. Okay, 60 read newspaper A, 50 read newspaper B, 30 read newspaper C, and then 20 read both A and B. C read 15 read both A and C. 10 read both B and C. 5 read all 3, right? So what are we trying to find? We are trying to find how many read at least 1 newspaper. How many? Okay, here are the steps. The first step is to define the set and regions, right? Setting up the Venn diagram. Set A is a set of people who read newspaper A, and then B, and then C. Okay, for newspapers A, B, C. Then you have the universal set for all the people surveyed, and there were 100 people surveyed, so your universal set is 100. Now the cardinality, the number of people in each set given. The total number in set A is 60, in B 50, and C 30. For A intersection B, okay, you have 20, and then A intersection C you have 15, and then B intersection C you have 10, and those who read all the three you were given 5. Okay, the next thing is you now draw your Venn diagram. You know the universal set is 100, and you are given what you are given is the those who read all the three newspapers A, B, C. The number is 5, so this is the region, so you write 5 there. But the other regions you don't know, okay, so you give letters. Those who read the newspaper A only should be A, and then this one B, and then for those who read newspaper C only, we put C, and then we have D here, we have E here, we have F here. And for those who did not read any of the newspapers, that is the outside region, so we give letter X there. Okay, moving on. You see, so this is what I explained, that A is for only A, B for only B, and on till X for none of them. So now we want to find those who read A and B without C. You see, those who read A and B only without C. Now here is the important thing you should know. This number that we are given for those who read A and B, okay, that is n number of A intersection B. This 20 that we are given as the intersection of A and B, it includes A and B only and all the three. You see, it includes A and B only and all the three, meaning some of the people in this 20 read A and B only. Some of them read A and B and C. So we have to remove those who read A and B and C to leave us with those who read A and B only. This is very important. So in the calculation process, you say, okay, number of students who, number of people who read A and B is equal to those who read A and B without C, that is C complement, and those who read A and B with C. So the total is 20. Those who read A and B without C, we put letter D there. Well, let's go back to the region. Where is D? Can you see? This is okay, it's very important. From here you can understand even better what I just explained. A and B, right? Look at this is the circle for A, and it meets with B. Now the region for A intersection B are 2. You see, this and this. Okay, this region is for intersection A and B and C, and then this region is for intersection A and B only. So the 20 that we are given includes these 2. Okay, is for the total of these 2. D and 5 gives 20. So we proceed to find that D. So we were given 20. Those who read A and B only without C, we don't know, we put D, plus those who read all the 3, we were given 5. So from here our D is the 20 here minus 5, we have 15. So those who read A and B without C, they were 15 students. So we proceed to the we go to our Venn diagram and write 15 in that region. Can you see? So if you add 15 to 5, you will get 20, right? So we are done with this. Then we move on to the next region. Here is the update. A and B only is 15. So now we want to get A and C only. A and C only without B. So remember again that the 15 that we were given for A intersection C includes those who read A and C only, and those who read all the three, A, C, and B. So let's go to the diagram again. Look at it. A and C. This is set A, right? And this is set what? This is set C. The region for A intersection C, can you see this is your set C, right? And this is your set A, right? So A and C, you see, you have this region for A and C. For all the three, and for A and C only. This one doesn't include B, and this one includes B. What we want to find is the region that does not include B, only A and C, right? But we were given the total here in the question. So we say E plus this 5 is equal to the total given. That is what is meant. So here you can see that A intersection C means those who read A and C without B, in addition to those who read all the three. So the total that we were given here is 15 equals those who read A and C only is E. We don't know that, so we are going to put E, plus those who read all the three is 5. Now our E is equal to 15 minus 5, and then E is equal to 10. Right? So now we know that the region for those who read only A and C is 10. So our result, we got 10. We proceed to the Venn diagram and put 10 in that region. So we are done with this region. So the next one is we're going to find this F for B and C only. And remember, the number we were given includes this 5 as well, because B and C, B intersection C, you see it has two regions here, right? For B and C only, for B, C, and A. So we are going to find this F. Okay, so find B intersection C without A, meaning B and C only. So we are given B intersection C as 10, and this 10 includes B and C only and all three sets. So here is the calculation. The number of elements in B and C, okay, B intersection C includes those who read B and C without A and those who read all the three. So the total we are given was 10 is equal to F, we don't know this, plus for all the three 5. So our F is 10 minus 5, we get F as 5. So we go to the Venn diagram, our result, we got 5. We go to the Venn diagram where we had that F, we put 5. See? So our update here is that B and C only is 5, right? So we put 5 there. Now we remain A, B, C. We want to find A, meaning A only without B and C, B only without C and A, and then C only without A and B. So this makes sense, and this is the easiest one because we were given the total for A, right? So if we want to find A only, we will just add all these and subtract them from the total that we were given. So this will give us our A. Okay, so this means this circle for A, for example, includes A only, A and B only, A and C only, and then all the three. If you go to B, the total for B is B only, B and A only, B and C only, and then all the three. If you go to C, you have C only, C and A only, C and B only, and all the three. This will now help you get the remaining unknowns. So how do we find A only? So they said given, we were given this N of A, those who read newspaper A, their number was 60. So this 60 includes only A and B only, A and C only, and all the three. Do you see that? So you write that in a mathematical equation. Number of those who read A, you see, newspaper A is equal to A only. We don't know that, so we put A plus A and B only. That is A intersection B without C, and then A and C only. A intersection C without B, and then all the three. You see, so A and B without C from there is 15. A and C without B, it was 10, and then A, B, C, all the three was 5. So if you add this one, you bring the 60 here, you bring is equal to A, plus then you add all these 15 plus 10, 25 plus 5, 30. Now your A is this 60 minus 30, and that is 30. So you go to your Venn diagram, see your update is that those who read newspaper A without reading B and C, their number was 30. So you go to the region for A only and put 30. See that? Next, we are going to find B, those who read newspaper B only. So only A, okay. Oh wow, update only A is 30. So the next step is find B only without A without C. How do you calculate that? Calculating region B. Remember the total that you were given for those who read newspaper B as 50. This 50 includes only B, A and B only, B and C only, and all three. So this means that my N into B is equal to B only, I don't know, then A and B only, you see, A and B without C, B and C only means B and C without A, and then all the three. So for this here, our numbers from the Venn diagram, we calculated that already. For A and B without C, we got 15. For B and C without A, we got 5. And for all the three, we were given 5. So we bring the 50 here is equal to B, we don't know, plus 15 plus 5, 20. 20 plus 5, 25. So our B will now be 15 minus this 25, and we got 25 as our result. Interesting. So this means that our result will just be 25. So we go to the region for B. The region for B, we put 25. Then we are going to get our region for C in the same way. You see, update our B, only B is 25. So we are going to find C only, right? Remember the number for those who read newspaper C, we were given 30, and this 30 includes only C, it includes A and C only, and it includes B and C only, and then all the three. So in the same way, we don't know those who read only C, so we give it a letter C. So number of those who read newspaper C is equal to only C, A and C without B, B and C without A, and all the three. So the values for this are all placed here. If you add these numbers, 10 plus 5 plus 5, you get 20. So your C will be 30 minus this 20, and you get 10. So for all, for C only, you get 10. So you go to the region for C only and write that 10. You see, this is it here, right? So we write 10 for the for this region. So if you look at this, we know everything except this, except our X, right? Those who read neither, they didn't read A, they didn't read B, they didn't read C. That is represented by X. So how do we find that X? Finding X is the easiest, because we know that the total here should give us this 100. So we add everything that we have here plus this one outside and equate that to 100. That's how we can get our X, right? So to get neither A nor B nor C, that is those who read none, calculating region X, right? The sum of all regions must equal the total. So in calculation, this is what we are going to do. We say only A plus only B plus only C, plus A and B only, plus A and C only, plus B and C only, plus all the three, plus none. Here, this none here is our x that we don't know, and is equal to the total in the universal set. So if you go back and get these numbers, these are all the numbers that we got previously, plus x is equal to 100. 30 plus 25, 55, plus 10, 65, 65 plus 15, 80, then plus 10, 90, plus 5, 95, plus 5, 100. So you have 100 plus x is equal to 100. So your x will be 0 because 100 minus this 100 will give you 0. So the number who did not read any of these newspapers is 0, meaning all of them read at least one newspaper. Oh my God, these people, you know, what do they say? They are current. Yeah, they are current. Always stay informed. So we are going to write 0 here, right? We are going to write 0 here. The number is just 0. Red none is 0. Okay, red none is 0. So if we want to find the number who read at least one, it means we have to unite A, B, and C, right? We have to unite those who read A, who read B, who read C, right? That is the meaning of at least one newspaper. So answering the original question says at least one newspaper, and it means A union B union C. So method 1 is to just add to add all the regions there, 1 2 3 4 5 6 7. You see, you add them 7 regions, okay, because the 8th one is outside. Right? So all the regions that you have here at least read 1 or 2 or all the newspaper. So you are going to have 100. Then you can also use another method, okay, which they call inclusion exclusion principle. Your A union B union C is equal to number in A, number in B, number in C, okay. Then you subtract the intersections, okay, of any 2 of them, and then you add the intersection of all the 3. So you subtract intersection A intersection B, A intersection C, and B intersection C. Then you add the intersection of all of them. So the numbers here, we were given 60, 50, 30. Then the intersection minus 20, minus 15, minus 10. And then the intersection of all of them was 5. We were given 5. If you do that, you will get that 100. If you do that, you will get that 100 again. Okay? Wow. So this is it. So another way of checking, remember we have already solved the problem. Here we are trying to see if our result is correct or not. A scientist, after obtaining his result, he doesn't just underline the result and say, oh my God, I finally got the answer. He has to verify whether this result makes sense or not, whether this result is correct or not, and that is what we are trying to do. So in the verification, we can also check the total. If we add all those who read 1, A, B, and C, okay, and then those who read neither, it should give us our universal set. So we found out that those who read all the 3, we got the total, the union, we got 100, plus those who read neither was 0, and this total will give us 100, and that is the total in our universal set. If you like, you can also check individually, okay. Those, remember they say those who read newspaper A was 60, those who read newspaper B was 50, okay. So that includes those who read A only, A and B only, A and C only, and then all the 3. You see, those who read B only, B and A only, B and C only, all the three. Those who read C only, C and A only, C and B only, all the three. And if you add all of that, you see that you get that number you were given in the beginning for each one of them. So this means that you are correct. Your result is correct, right? Also, the intersection for A intersection B, remember you have A intersection B that does not include C, and then A intersection B that includes C. So if you add those two, you will get the 20 that you are given in the problem. A intersection C is also twofold. You have A intersection C that does not include B. You have the one that includes all of them, okay? So that would be 15. B intersection C, you have B intersection C that does not include A, and then the one that includes all the three, so that will be 10. And you were given for this one, you were given, right, for all the three it was 5. So you were right. So and finally, here is our complete solution with all the regions given their appropriate numbers, right? We did justice to all of them. Answer to the question. Remember, the question say we should get those who read at least one, right? So we have to unite those who read all the three. So we got 100 people read at least one newspaper. All here is the note: all 100 people read at least one newspaper. None read 0 newspapers, because we got 0 for the outside region, right? Wow, amazing. We have come to the end of this lecture on Venn diagram and set in general. Okay, thank you for your attention. This is the end of our today's video, and I look forward to seeing you in the next one. Stay tuned for the next. Thank you very much. Assalamu alaikum wa rahmatullah.